Welcome back to this next video in which we are trying to prove that a finite multiplicative subgroup of a field is going to be a cyclic group. Okay, so remember, to do this we are proving this relative theorem from group theory, which is that if you have a finite group which obeys this property that no matter what little d you pick, which divides the order of the group little n, there exists at most d solutions to the equation x to the power of d is equal to 1. If it obeys that property, then you can instantly conclude that your group is cyclic of order n. Okay, and that's what we're trying to prove. And of course we've discussed why proving that would then prove that if you have a finite multiplicative subgroup of a field, it's also going to be a cyclic group, because indeed finite multiplicative subgroups of a field would obey that property. Okay, so how are we going so far? So what we've done is we've used this property here to so far conclude that G has all normal seed-off subgroups. Okay, so for every single prime in the prime factorization of the order of your group, if it obeys this property, then it's going to have all normal seed-off subgroups, i.e. For each of the primes in the prime factorization of the order of the group, the seed-off subgroup relating to that prime is unique. There's one and only one. Okay, so they're all normal inside the group capital G. We've also discussed the fact that if you take any two of these and intersect the two of them together, you are going to get the trivial subgroup. Okay, and finally we ended the previous video by saying that this meant that your group capital G, we could conclude that it would be isomorphic to the direct product of all of its seed-off subgroups. Okay, right. Now, this is where the concepts of internal direct product and external direct product are going to become important, because those of you that are familiar with internal and external direct products will remember that this looks awfully like the conditions for where we can talk about internal and external direct products. We have all normal subgroups in capital G, where their intersections are the trivial subgroup. Okay, and here, this is in fact what we could call the external direct product. Now, even in the video on internal and external direct products in the playlist on group theory, we only talk about it in the context of two groups. Here it's more generalized, we're talking about it for S subgroups. Okay, so what I want to do is firstly just give you a little reminder of how it works for just two subgroups, and then show you how it's going to generalize to this higher case, and therefore explain to you why this statement is actually true, and truly why we care so much that this statement is true, how this means that the structure of our group is actually extremely simple. Okay, right. So firstly, let me remind you of how it works for just two subgroups. Let's just say that we've got P1 and P2 here. Okay, so the seed-off P subgroup for P1 and the seed-off P2 subgroup for capital P2 here. Okay, so we know that both of these are normal subgroups of capital G, and we also know that the intersection of these two is equal to the trivial subgroup. Okay, those are the two conditions that you need your subgroups to obey in order to talk about the internal and external direct products of these two subgroups. Okay, so what you can then do is you can take the subgroup product of these two subgroups, so P1 producted with P2, and in this case, when the subgroups obey these properties, this is called the internal direct product rather than just the subgroup product. And the reason is that we know that this ends up isomorphic to the direct product of these two subgroups. So you can direct product the two subgroups together, and in this case the direct product of the two will be called the external direct product of the two subgroups to exaggerate the differences between the two. Okay, right. Now, I'm not going to prove this result here. I'm going to refer you to the video on internal and external direct products, but let me just discuss in a little bit more detail the structure of this. So remember, the internal direct product of P1 with P2, this consists of all elements of the group capital G of the form little x1 composed with little x2, where little x1 is an element of capital P1 and little x2 is an element of capital P2. Okay, so you take every element of capital P1 and compose it with every element of capital P2. Okay, what does this being isomorphic to the direct product of the two mean? Okay, well firstly it means that all of these answers are distinct elements of the group capital G. No two different compositions of an element from capital P1 with an element from capital P2 are the same. Okay, they are all distinct elements in here. In addition, what it tells us about is how to compose elements in here. Okay, so if you've got little x1, little x2, and you want to compose it with little x1 bar, little x2 bar, so you've got these two elements of your internal direct product here. Okay, well, because we know it's isomorphic to this, we know how composition works here, it's just component-wise. Okay, so what this tells us is that this is actually just going to be x1 composed with x1 bar, so compose the two components from capital P1 together, and then composed with x2, x2 bar, like so. So compose x2 and x2 bar together. Okay, and in the video on internal and external direct products, we proved that the reason for that is that you can prove that if these conditions are true, elements from capital P1 commute with elements from capital P2, so you can just switch the x2 and x1 bar around there, even if the group isn't abelian. Okay, these conditions make it so that elements of capital P1 will commute with elements of capital P2, and that's how composition in here ends up isomorphic to what you'd get if you just direct producted these two subgroups together. Okay, so truly you end up with the same algebraic structure. They are isomorphic to one another, and that's why this subgroup product is now called the internal direct product, to show how the structure that you end up with is the same as what you would have got if you direct producted the two together. It's called the internal direct product because we're using an internal, in nature, way of producting the two subgroups together, a way that relies on you understanding that they are inside some larger group capital G. This one is then exaggerated and called the external direct product. This is the true direct product, if you like, because here you didn't need to think of them as being inside of a larger group capital G in order to construct that, hence it is external to the group capital G. Okay, but essentially the algebraic structures end up identical. And why this is so nice is because this is extremely simple. This component-wise way of composing elements, that's extremely simple, whereas normally in a subgroup product the composition can be much more complicated. But in this case, where we're talking about internal direct products, the composition ends up extremely simple, isomorphic to the external direct product. Okay, right, so that's what we cover in the video on the internal and external direct products, and we prove all of this. We prove this isomorphism. What I now want to do is generalize it. I want to show you how to do this now for free subgroups that are all normal and which have intersections with each other, the trivial subgroup. And then I hope that by doing it for free you will get intuition for the fact that you could just keep going and you could do it for an arbitrary finite number, and therefore you could do it for all S of the normal C of P subgroups, or C of subgroups rather, which all have trivial intersections with one another. Okay, so let's now extend this to the free case. So what I now want to do is bring P free into the fun here. So P free I know is a normal subgroup in capital G. Okay, what I now need to prove, because what I want to do is I want to take the internal direct product of P free with P1, P2. But what I need to prove is that I can even talk about this. I need to prove that both of them obey the necessary conditions. I know this is a normal subgroup. Do I know this is a normal subgroup? Well, I need to prove that. I also need to know that the intersection of the two is the trivial subgroup, to know that I can internal direct product them. And then, of course, I can say that that will be isomorphic to the external direct product, and we'll discuss the intuition for all of that. Okay, so the first thing I want to prove then is that the internal direct product of P1 and P2 is going to be a normal subgroup in capital G. Okay, right, and this is in fact a more general point that works for more arbitrary groups than necessarily these Seelof subgroups. Okay, so this comes from the fact that the two things which we producted together were both normal in G. Okay, so to prove this, what we need to prove then is for all little g is an element of capital G, we need to prove that if we use little g to conjugate the internal direct product of P1 with P2, like so, that we end up with the same thing back again, the same subgroup P1, P2 back again. Okay, so this is what we want to prove. Now, how are we going to do that? Well, remember we're dealing with finite group theory. This is a finite subgroup of capital G. Okay, so this shouldn't be too difficult because we know that if we were to conjugate all of the elements of capital G by little g, that would constitute an inner automorphism of capital G and would certainly be a bijective map. Okay, so that means that when we restrict the map down onto this subgroup, the internal direct product of P1 with P2 of capital G, the map is still going to be injective. So all we actually have to prove is that all the elements of capital P1 internal direct product with capital P2 are actually going to be mapped back into the internal direct product of P1 with P2 by conjugation by little g. Okay, we don't need to worry about surjectivity because it's finite. So if we've got an injective map that's sending everything here into here, the only way that that's possible is if it is surjective, and therefore it's a bijective map. Okay, so all I need to show is that if I take an arbitrary element of here, which will be little x1 composed with little x2, that this is going to be back inside there, that this is going to be an element of the internal direct product of P1 with P2. So how can I prove that? Well, just by a clever trick here, just inserting in the middle G inverse and G. Of course this has no effect at all because those two cancel, like so. But why is that an ingenious trick? Because look, here is a G conjugate of little x1, and here is a little g conjugate of little x2. Okay, little x1, remember, is an element of capital P1, which is a normal subgroup of capital G. So this is going to be some little x1 bar, some other element of capital P1. And here we have a little g conjugate of little x2. Again, because capital P2 is a normal subgroup, this is going to be some little x2 bar here. Okay, some other element of capital P2, i.e., this is going to be an element of capital P1 composed with an element of capital P2. Okay, therefore it's still going to be in the internal direct product of capital P1 with capital P2. So there is the simple reason for why the internal direct product of these two normal subgroups of capital G is always going to itself be a normal subgroup of capital G. Okay, right, so what that now means is that the first condition is satisfied. These two subgroups that I have of G are both normal in G. All I now need to verify is that their intersection is equal to the trivial subgroup, and then I can internally direct product them, and it will be isomorphic to their external direct product. Okay, so why is this going to be the case? Well, think of the orders of these. Okay, same argument as we've seen before. The order of the internal direct product of P1 with P2 is just going to be the order of P1 times the order of P2. Okay, because think about this, you've got the order of P1 elements that you can put in the first slot, and for each of those you've got the order of P2 elements that you can put in the second slot. So the order of this is just going to be the order of capital P1 multiplied by the order of capital P2. Okay, well, because they're the Seelof subgroups, we know what their orders are equal to, so this thing is going to have order P1 to the power of alpha 1 times P2 to the power of alpha 2. Meanwhile, P3 will have order P3 to the power of alpha 3. Is there anything except 1 that can divide both of those things? Well, of course the answer is no. Look at their prime factorizations, they're completely distinct, they involve completely different primes. Okay, so indeed the subgroup, the only subgroup that you can get here is the trivial subgroup. So Lagrange's theorem helps us out again here. Okay, so indeed we can conclude that the intersection of these two is the trivial subgroup, and therefore what we can now consider doing is taking the internal direct product of P1, P2 here with P3. Now, strictly speaking, I should put brackets initially around here because we're taking this subgroup and internally direct producting it with this one, but I will drop that. Okay, and let's have a little bit of intuition as to what this actually is going to be. Well, this is going to be the subgroup that contains all elements of the form x1, x2 composed with x3, and now you'll see why I can drop the bracket, because all putting the bracket there would mean is putting brackets around this, but of course we know group composition obeys associativity, so we don't need to worry about that bracket. Okay, so x1 is an element of capital P1, x2 is an element of capital P2, and x3 is an element of capital P3. Okay, and what we are now given is that this is going to end up isomorphic to the external direct product of P1 with P2 with P3. Okay, so it's going to end up isomorphic to this, P1, P2 direct producted with P3, but of course we know that this is isomorphic to P1 direct producted with P2, so this is just going to be P1 cross P2 cross P3, I hope you'll agree, which is all ordered triplets. So this, just to give you some intuition here, this will be all ordered triplets, x1, x2, x3 here, where x1 is an element of capital P1, x2 is an element of capital P2, and x3 is an element of capital P3. Okay, like so. Okay, so let me just add a bit of colour on this, because this has become distinctly colour lacking. Okay, so here is the internal direct product of these three subgroups here. Okay, and here is the external direct product of those three subgroups here, and I'll just move this up to try and get it in better view. Okay, right. So what this is really telling us is that composition here is extremely simple. This structure is extremely simple because it's isomorphic to this structure here. Okay, so each one of these compositions is unique. Okay, there is one representation for each element that is in here and one representation alone, i.e. you cannot come up with different combinations of an element from capital P1, an element from capital P2 and an element from capital P3 which would give you the same element of capital G. These are all distinct, okay, just like the ordered triplets are all distinct and they correspond to their ordered triplet here. In addition, composition in here is just like it is over here. So if I take one element here and want to compose it with another element which is of this form as well, an element from capital P1, an element from capital P2, an element from capital P3, all I have to do is component-wise. Compose the two elements from capital P1, compose the two elements from capital P2, and compose the two elements from capital P3. Okay? It's beautiful. It's very, very simple. And now, of course, I hope that doing this has now given you the intuition for the fact that you could go further. You can now internal direct product this with P4 and it would end up isomorphic to P1 cross P2 cross P3 cross P4 and so on. Okay, so what you would overall be able to do is take the internal direct product of P1, P2 all the way up to PS and it would end up isomorphic to the external direct product of P1 with P2 all the way up to PS, which is really telling you that all of these different compositions, all of these different combinations of an element from capital P1, an element from capital P2, all the way up to an element from capital P3, they are all distinct elements, just like the triplets are all distinct elements, and that if you want to compose any two elements, everything just commutes with everything else because of the fact that they're all normal and their intersections are all the trivial subgroup, okay, and therefore you can just do it component-wise, just take the elements from capital P1, compose those two together, take the elements from capital P2, compose those two together, all the way up to PS here. Okay, so incredibly simple structure here. Now, think of what the internal direct product of P1 with P2 all the way up to PS is equal to. Well, this is equal to the entire group, okay, because what's the order of this? It's going to be the order of capital P1 times the order of capital P2 all the way down to the order of capital PS. This will give me P1 to the power of alpha 1, and I'll just move this down a bit. This one will put in the P1 to the power of alpha 1, this one will put in the P2 to the power of alpha 2, all the way down to this one putting in the PS to the power of alpha S. So indeed, this internal direct product of all of these S C-log subgroups is going to give the entire group, and therefore the entire group is going to end up isomorphic to the external direct product of all of these C-log subgroups. P1 with P2 all the way up to PS. And really what I would like you to think of this, what I would like you to understand by this, is that all of the elements of the group can be written as an element from the first Ceilov P subgroup, or the first Ceilov subgroup pertaining to the first prime, composed with an element from the second Ceilov subgroup here corresponding to the second prime, all the way down to the S of Ceilov subgroup here corresponding to PS. Okay, and the composition is extremely simple. It's just component-wise in the way that it's component-wise over there. That's what this statement is really saying. It's showing you how the structure of this group that obeys this bizarre property that we started off by stating is extremely simple. Okay, right. We'll again have a break here, and in the next video what we will do is prove that each of these Ceilov subgroups is actually cyclic itself. And then what we'll do is conclude that overall, because now the entire group is isomorphic to the direct product of these Ceilov subgroups, and all of the Ceilov subgroups are cyclic, that implies the entire group is cyclic.